Sure.
Hello, everyone. Thanks a lot for joining us today. Our speaker is Matija Bucić from ETH, and he will talk on tournament quasi-randomness from local counting. During the talk, if you have any questions, please write it in the chat. If it's something urgent, I'll raise it to Matija. Otherwise, we will delay all the questions to the end of the talk. Okay, Matija, you can start.
Okay. Thank you very much. So thank you all very much for zooming into my talk. And big thanks to the organizers for giving me the chance to speak. Today I'm going to talk about forcing tournaments to be quasi-random by counting subtournaments. Everything I'm going to say is joint work with Ian Long, Asaf Shapira, and Benny Sudako. Okay, so let me begin by telling you what happens in the undirected case. So here, for me, on an intuitive level, a graph is said to be quasi-random if it behaves like a random graph in terms of some deterministic property. So let's look now at a more formal definition. This one is due to Chung, Graham, and Wilson, and they say that a graph is quasi-random if for any subset of its vertices, when you look at the induced subgraph that these vertices make, what you see there is about half of the possible number of edges. So this is certainly something that we expect the random graph to satisfy. And also this is a deterministic property. So this definition does fall under the umbrella of the intuition that I gave at the start. Now, quasi-randomness in general has been studied for a long time, but systematic study was initiated by two papers, one of Thomason and one of Chung, Graham, and Wilson in the late 80s, when this was the first systematic study of quasi-randomness. So one of the main or most useful outcomes of these early papers is that they showed that there exists a large number of mutually equivalent definitions of what it means to be quasi-random. Now, why is this so useful? Imagine that you are working with a graph and you can verify one of the conditions of these definitions. Then immediately you can conclude that all of the definitions hold, so you have a large arsenal of properties coming from all these definitions that you can use. So what this really means is that as soon as you can check one of them, you can work with your graph much more closely as if it were actually a random graph. So this is what makes these multiple definitions useful. And in this talk, I'm going to look at some definitions of this sort that arise from counting sub-objects. So let me show you an example. So this is yet another of the classical definitions of Chung, Graham, and Wilson. It's equivalent to the one on the previous slide. So they say that an n-vertex graph is quasi-random if it has about half of the possible number of edges and if it has the correct number of C4s. And what do I mean by correct number of C4s? Exactly what you would expect to see in the random graph Gn1/2 on the same number of vertices. And everything I'm going to be saying is always up to lower order terms. So this is necessary for all of these definitions to make sense. Okay, so now this definitely consists a counting definition of quasi-randomness, and Chung, Graham, and Wilson already raised the question, well, what kind of things can you count in order to guarantee quasi-randomness? So for example, they observed that if you replace C4 with a triangle, then suddenly it is no longer true. So this definition does not work with a triangle in place of C4. They give an example of a graph which has correct count of both edges and triangles, and yet isn't quasi-random. Okay, so they raise, following this, a natural question, which is, what kind of families of graphs have the property that if you have correct count of each graph in your family, then you are forced to be quasi-random? So they call this kind of families forcing or quasi-randomness forcing. And over the years, there has been a lot of study of these kind of families. So a lot is known and a lot is not known. So let me just mention the two latest groups of people who have a paper on this. So one is Ryer and Schacht, the other is Hubay, Kral, Parchik, and Persson. So if you look at all these papers, one thing that you'll observe is that they always look at forcing families, which have at least two graphs. Now, for example, in our definition above, we were counting both edges and C4s. And in this not example, we were counting edges and triangles. So the reason for that is that counting a single graph is never going to be enough. There is a very simple example showing this. So you start with n vertices, isolated vertices, and then you start increasing the size of a clique among these vertices. And at the beginning, you had 0 copies of your graph. And once your clique becomes all n vertices, you have more copies than you would have in a random tournament on the same number of vertices. So at some point in this process, you have hit a point at which you have correct count of your graph, and yet you are still consisting of a clique and a bunch of isolated vertices, which is very much not quasi-random. So this never works. And it was Simonovits and Sós who were the first to observe the real reason why you can never count just a single graph. And the reason is that being random is a hereditary property. So what does this mean? If you are a random graph and I look at a linear sized subgraph, say, what I expect to see there is still a random graph. So somehow randomness should be hereditary. It should work on the subsets as well. And this kind of single counts can never capture this concept. So what they suggested is, instead of just counting the total number of copies that we see, why don't we just count as well, or insist that we have correct counts in any linear sized subgraph as well? So this is what they call having correct local counts of a graph. And this turns out to be a more interesting question. So in this setting, Simonovits and Sós showed that actually, if you have correct local counts of any graph, you are immediately forced to be quasi-random. So any graph is forcing quasi-randomness in this way. Okay, so in this talk, I'm going to be looking at this kind of problems in which you want to count a single object and you want to force quasi-randomness. So here we've seen what happens. So let me show you another example. So still in undirected graphs. So on the previous slide, we were always counting subgraphs as not necessarily induced subgraphs. So we didn't care whether we find our C4 as an induced copy or not. So now let's change this. So another of the classical definitions of Chung, Graham, and Wilson says that the graph is quasi-random if it has correct counts of all h-vertex graphs for some fixed h bigger than 4, but this time as induced subgraph. So this is once again equivalent to all the other definitions I've so far given you, but this time it looks at induced copies. Okay, so once again it makes sense to ask what happens if you want to count a single graph instead of all the h-vertex graphs. And yet again, unfortunately, the answer is still no. The reason is the same as before, but now you need to actually work a little bit harder to actually build a counterexample. But you can still do it. So once again, the correct question to ask is, what happens if we also assume that we have correct local counts? And this was once again looked at by Simonovits and Sós, who showed that if you have correct local counts of a regular graph H, then you are forced to be quasi-random. They also conjecture that also in this case, it's always true that having correct local counts implies quasi-randomness, with the exception of a P4, of the path on 4 vertices. So in this setting, the answer is more interesting, and this conjecture is actually still open, and a very nice problem, one of the main actually open problems surrounding this kind of questions. And for this talk, I want to look at analogous problems, but in tournaments. Okay, so let me now say just that quasi-randomness has been studied in a variety of different settings. Pretty much whenever you have a natural random object, there is an interesting quasi-randomness theory. So in this talk, I'm going to be focusing on tournaments. And so let me just make it clear what I mean by the random tournament, what we are going to compare with. So the random tournament Tn1/2, you get by taking a clique on n vertices and then orienting each edge of this clique uniformly at random. Okay, so this gives us a tournament, and this is what I mean by the random tournament. Very good. Now, Chung and Graham defined what it means to be quasi-random tournament. So they say that a tournament is quasi-random if for any ordering of the vertices, you see about half of the edges respecting this ordering, meaning they go from a smaller point in the ordering to a bigger point in the ordering. Okay, so this definition, and the first to study quasi-random tournaments were Chung and Graham, only a few years after the original quasi-randomness definition. So as in the undirected case, for tournaments, there is once again a big number. Specifically, they give 11 equivalent definitions of a quasi-random tournament in their original paper. So once again, we are going to look at definitions of alternative, or some of these actually even definitions of what it means to be a quasi-random tournament, but in terms of having correct local or global counts. So let me introduce some notation. So by nh of t, I denote the number of labeled copies of h as a subtournament of t. Okay, so here, don't worry too much about labeled versus unlabeled. The only difference is you divide by the number of automorphisms. And what we actually care about is we are only going to be comparing this function for an arbitrary tournament t with this function for the Tn1/2. So whether you include automorphisms or not, they're just going to cancel out. Okay, I chose to talk about labeled because it gives me slightly nicer numbers. So let's look at an example. So for example, the nh of Tn1/2 is equal to 2 to the minus h2 times n to the h plus lower order terms. So where is this coming from? So this expression on the right is just the expected number of labeled copies of h we expect to see here. And to see this n to the h comes from you take our tournament h, and for every vertex, you decide where you want to see it in the Tn1/2. So this you can do in n to the h many ways. And now you're wondering what is the probability that at this position you actually see h. And this probability is simply 2 to the minus h choose 2, because between any two vertices at this position, you need to see the edge oriented in the same way it was in h, which happens with probability of half, regardless of how h was oriented. Okay, so I just did this computation once because you are going to be seeing this number a lot from the rest of the talk. So it just means correct number of copies of h in the random tournament. Okay, so now let me give you another classical definition of Chung and Graham of what it means to be a quasi-random tournament. So this one is in terms of some counting, so closer to what we want to look at. It says that if you have correct counts of all h-vertex tournaments for some fixed h bigger or equal than 4, then you are quasi-random. And let me once again say what I mean by having correct counts. I mean that you see exactly the same number as you expect to see in the random tournament, once again, up to lower order term error. Okay? So in this setting, again, it's interesting to ask, well, can we just count a single tournament instead of all h-vertex ones. So let's define this. So let's say that a tournament is globally forcing if having correct count of h implies quasi-randomness. Okay? So in other words, if in the above definition, you can replace all h-vertex tournaments with just this h. So this is what it means to be globally forcing quasi-randomness, if you. Okay? So we've seen in both undirected settings that actually the answer was no, such things do not exist. And in this setting, the answer is more interesting. So they do exist. And it's actually an exercise in Lovas's book, Combinatorial Problems and Exercises. And it was recently reproved using flag algebras by Corellano and Razborov that any transitive tournament on 4 or more vertices is globally forcing. And what I mean by a transitive tournament, it's a tournament in which you fix some ordering of the vertices, and then all the edges are respecting this ordering. So this is a transitive tournament. And now, given this result, the question is, well, are there more globally forcing tournaments? And if yes, how should they look like? So our first observation is that actually they do not exist, at least if you have 7 or more vertices. So we showed that H is globally forcing if and only if H is transitive, provided H size is at least 7. Now you might be wondering why I'm repeatedly saying this at least 7 vertices. And the answer is it's actually necessary. So Corellano, Parente, and Sato showed that there exists a 5-vertex non-transitive globally forcing tournament. So you need a restriction of this sort in some sense. And actually following our work, using some of our ideas and some new ideas, Hancock, Cabela, Kral, Martins, Parentes, Kerman, and Volets have shown that on 5 and 6 vertices, this 5-vertex exception is the only exception. So combined with our general result above, this means that you are globally forcing if and only if you are transitive or this 5-vertex exception. Okay? So now let me show you how we prove this result. So this is not the main part of our paper, but it is an easy proof, but I decided to include it because it's nicer to present it, and it's also describes some concepts that we are going to look at very well. Okay, so let me show you how we do this. So I want to show you that any non-transitive tournament H on at least 7 vertices is not globally forcing. So what this means is I need to find you an arbitrarily large non-quasi-random tournament which has correct counts of H. Okay, so this is the task. Now let's see how we go about doing it. So we take our H and we take a blow up of H. And what I mean by this is I replace every vertex of H with a blob of size n over H. And then between any 2 of these blobs, I orient all the edges to go in the same direction and to go in the same direction that the original edge of H went. Okay, so this is just a usual blow up. But also I need to make B to be a tournament. So within the blobs, I order the edges arbitrarily. It doesn't matter for the argument. Okay, now why does this make sense? Well, I claim this B actually has a lot of copies of H. So let's see what I mean by a lot. Well, for any vertex of H, you can choose a representative in its blob in n over H many ways. And when you do this, you always end up with a labeled copy of H, just because how we build the blob. So this means that in total you get at least n over H to the power H, which is the size of H, so how many vertices, labeled copies of H. Okay, And now, why is this a lot? And what do I mean by a lot? Well, it's bigger than what you expect to see in the random tournament. At least provided h is at least 7. And here is where this h is at least 7 comes into play. So this inequality, at least that for big enough h it holds, it's easy to see because this guy is of order 2 to the h squared, and this guy is of order 2 to the h log h. So if h is big enough, this inequality is going to be true, and big enough just turns out to be h at least 7. Okay, so once again, so far we've found a tournament which has more copies of h than the random tournament on the same number of vertices. But we need to find a tournament which actually has correct number of copies, not more. And there is a neat trick which lets you pass from this whenever you have a tournament with more copies to one which has correct number of copies. So let me show you how this works. So first, pick an ordering of the vertices of our blowup. Then take the first vertex in the ordering and reorient all of its edges to respect the order. Okay. Now move to the second vertex. Once again, reorient all of its edges to respect the order. And you do this for every vertex. And what you end up with is a transitive tournament. Okay? So what does this process do? We start with our blowup B, which had more copies of H than the random tournament. And we end up with a transitive tournament, which has 0 copies of H. And why does the transitive tournament has 0 copies of H? Well, any subtournament of a transitive tournament is itself transitive. And we are assuming that our H is non-transitive. So it can have no copies of H in itself. Okay, so once again, at the beginning of the process, we had more copies. At the end of the process, we had less copies. And it's not hard to see that at each step of the process, we don't change too much the number of copies of H that we see. So what this means is that by some kind of intermediate value argument, at some point of the process, we must have hit a tournament which had correct number of copies. Okay? So now what remains to be done is that this intermediate point tournament actually isn't quasi-random. And this is pretty trivial because if we did too many steps of our procedure, then at the beginning of the tournament, you've already built a big transitive tournament. And this is not a quasi-random property. Similarly, if you did too few steps, then you look very similar to our original blowup. And in particular, you can find 2 linear sized subsets such that all the edges are oriented from one to the other, which again is not a quasi-random property. So to summarize, we've found a tournament which has correct number of copies of H and which is not quasi-random, which is precisely what our task was. So this shows that H being non-transitive, at least 7 vertices, is not globally forcing. Very good. So this completes the picture on global forcing. But we've seen in both undirected cases that actually when we did this local counting problem, we got much more interesting answers and many more tournaments which work. Well, graphs in that case. So let's look in this setting as well. What happens if instead of just requiring to have correct count in our big tournament, we also want to have correct count in sub-tournaments. So at this point, I just want to mention that these kind of problems were considered in addition to the 2 settings I've shown you already by Simonovits and Sós, also in hypergraphs by Conlon, Hahn, Persson, and Schacht, and Della Monica and Rodel, and also in directed graphs, this is in preparation, by Fox, Himwich, and Mann. So people looked at these problems, and in general, they have some interesting behavior. So let me once formally state what I mean by having correct local counts of H. So for me, this means that if you take any subtournament and you count the number of copies of H that you see there, you see exactly the same number as you would expect in the random tournament of size same as T prime, up to an error of little of n to the H, where n is the size of the big tournament. So what I want to point out here is that if T prime is of size sublinear in T, then this condition is just immediately satisfied. Simply because any sublinear tournament can have at most little of n to the H copies of H. At most, even if every possible location has a tournament. So that means that it just falls under this error that we put here. So in other words, having correct local counts is in some sense equivalent to saying that any linear sized subtournament has correct global counts, or correct counts in our previous definition. Okay, so now let's define the analogous forcing concept in this setting as well. So here we say that H is locally forcing if having correct local counts of H implies quasi-randomness. Very good. So now an immediate observation is that global forcing implies local forcing. And the reason is, if you have correct local counts, this includes having correct global count. You just plug in T prime equals to T in this definition. Okay? So the actual question that we want to look at here is if there exist any additional tournaments which are locally forcing but not globally forcing. And if you play a little bit with it, if you look at small examples, very quickly you'll get the answer to this question. So actually, any free vertex tournament is locally forcing, and neither of them is globally forcing. Now, the problem is that the way you show that they are locally forcing relies crucially on the fact that there exist only two different free vertex tournaments. So this helps you a lot in this counting. You cannot get two crazy things happen. But as soon as you move to 4 or more vertices, it becomes immediately not obvious how could you show this kind of locally forcing property. So really the main question and the interesting question that we want to look at is, what do large non-transitive locally forcing tournaments exist? So this is the equivalent. So we've seen that in the undirected cases, the answer to the analogous question was a resounding yes. So in the first case, all of them were proved to be locally forcing. And in the induced case, it's at least conjectured and widely believed that actually any graph is locally forcing in that setting as well. Here, the answer turns to be, once again, quite different. And actually, you need to be very restricted if you want to be locally forcing. So this is the topic of our first result, which tells you how you need to look like if you want to have a chance to be locally forcing. So let me show you what we get. So we proved that if you want to be locally forcing, you need to be nearly regular. Where by nearly regular, what I mean is that you satisfy this slightly nasty expression on the slide. Okay, so now this immediately tells you that the analog of the Simonovits-Sós conjecture does not hold in the tournament setting. So there are many, many tournaments which are going to be failing this condition. And actually thinking about that setting, we've also seen there that they managed to prove that any regular graph is locally forcing. So we thought, given this near regularity condition for a long time, that actually the answer here should be that every regular tournament is locally forcing. And what I mean by a regular tournament a tournament in which every vertex has equal out degree and in degree. Okay? And it came as quite a surprise that this is not the case. You need to be way more restricted. So our second result says that for any ordering of the vertices, if you look at the number of edges which respect this ordering, it should be about a half up to an error of h to the 3/2 times root log h. So let me now tell you what this condition is actually saying. So if you replace this h to the 3/2 root log h with little of h squared, what you get is just the quasi-randomness definition that I told you a few slides ago. So in particular, this condition is telling you that you need to be very strongly quasi-random if you want to be locally forcing quasi-randomness, which is quite an interesting situation. So also to illustrate just how strongly quasi-random you need to be, there is a result of Spencer which says that for any tournament, there is an ordering in which you are going to be off by at least h to the 3/2. So this result is best possible up to this root log h factor in the error. Okay, so now the third and final restriction says something similar. So it says that if you take two disjoint, that if you want to be locally forcing, for any two disjoint subsets of your tournament, you need to have about half of the edges going from the first to the second, up to an error of constant times h to the 3/2. Once again, if you replace h to the 3/2 with little of h squared, you get yet another classical definition of quasi-randomness. And yet again, there is a result of Spencer, which shows that if you replace these two by a smaller constant, then you can find such subsets in any tournament. So in any tournament, you'll find two subsets which are off by at least constant times h to the 3/2. Okay, so now let me summarize what I told you in this slide. So I told you that if you want to be locally forcing, you need to be very restricted. So you need to be nearly regular, you need to be strongly quasi-random in two different ways. Okay, so now given this, remember our original goal was to find new forcing tournaments, more forcing tournaments. And these restrictions, so the natural question is, can we find a graph or tournament which does satisfy these restrictions? And since B and C seem to be very close to best possible, the natural guess would be to try to find something that satisfies B and C. And what is the most strongly quasi-random tournament that you know? Most likely the random tournament itself. And actually, there is a result of De La Vega, which says that the random tournament does satisfy both conditions B and C. Half, it fails A. So it is not nearly regular enough. So our next result says that TH1/2 is with positive probability not locally forcing. So in other words, what this is saying is that a constant proportion of all tournaments on H vertices are not locally forcing. And this is in stark contrast to both undirected cases we've seen so far, where it's known, or at least conjectured and widely believed, that all graphs should be locally forcing. Okay, so let me give you a very, very sketchy sketch of how we prove this result. So I already told you the main idea. The random tournament is not regular enough. So let's introduce the random variable.
Matija, sorry, could you remind us what locally forcing was?
Yes, sure. So locally forcing means that if you have correct local counts of the tournament H, which means in any linear sub-tournament, you see the same number of copies of H as you would expect in the random tournament of the same size. So if you have this property, then you are forced to be quasi-random. Okay? So once again, so here I'm not going to actually be going back to locally forcing definition. So it all comes, I'm just going to be using the condition from the previous slide. So if x counts the number of, so x is the random variable which takes the left-hand side of our near regularity condition minus the right-hand side of near regularity condition. And the only thing I want to say is that x will be positive with positive probability. So what do you do first? Well, you compute the expectation of this random variable. It's elementary calculation, which tells you that actually the expectation is 0. Very good. So this already should imply this in some sense, but except if x is some kind of weird pathological random variable. And how do you avoid such strange cases? Well, you look a bit at higher moments. So I'm not going to go into details. Let me just mention that you can rewrite x as a function of certain indicators, which makes it very easy for you to compute expectations and also higher moments, and also makes some readily available probabilistic tools applicable in this setting. Okay, so in total, if you trust me about this with higher moments, what this means is that you are going to be failing the regularity condition with positive probability, and our theorem tells you that immediately you are not locally forcing with positive probability. Okay? So far, I've told you that if you want to be locally forcing, you need to be very restricted, and also that the natural guess for what graph tournament should satisfy these restrictions, the random one, it actually doesn't. So at this point, we might start to despair. What happens if these locally forcing tournaments don't exist? This would be a disaster. So, but actually, the world turns out to be nice, and they actually do exist. So our next result is that not only they do exist, but there is quite a few of them. So let me show you how we generate some locally forcing tournaments. So we start with the partition of a clique on h-vertices into triangles and edges, edge-disjoint triangles and edges. So for example, here is a K5. We split its edges into triangles and edges. So in red, we have 2 triangles, and in blue, we have 4 edges. So now I'm going to generate a random tournament based on this partition as follows. So take each of the triangles and orient them cyclically in one of 2 possible ways, uniformly at random. So what this means is, let's look at this triangle. We either orient it to be a cycle in this direction or a cycle in this direction. Very good. So we do this for every triangle in the picture, and then we move on to the edges. So now we orient each of the edges uniformly at random. And so for example, in the picture, all of the blue edges, we just orient them at random. And very importantly, we orient each of the objects independently of all other objects. Very good. So this gives us a random tournament. And I claim that it does satisfy the restrictions that we've imposed on locally forcing tournaments. And why is that? Well, imagine for the moment that our partition consists only of triangles. Then I claim that no matter how you orient these triangles, you always get a regular tournament. Why is that? Well, when you oriented your triangle, you always added exactly 1 in edge and exactly 1 out edge at every vertex. So what this means is that the in degree and out degree changes by the same amount whenever you orient a triangle. And since we're only orienting triangles, throughout this orientation process, you are always regular. And in particular, you end up with a regular tournament. On the other hand, still most pairs of edges that you see in this picture were oriented independently. which allows you to show that you are still going to be quasi-random enough for our restrictions. So very good. So this tells you that at least if you're mostly using triangles, you satisfy our restrictions, but it tells you nothing about how you would actually go about showing that an object like this is locally forcing. And that is precisely the point of our next result. So we managed to show that as long as you are using only a small constant proportion of edges in this partition, this random process is going to spit out a locally forcing tournament. Okay? So also, the argument that we use is actually quite robust. So you can change a lot in how you're generating this. And also, since you can move these edges wherever you want, you actually get quite a lot of locally forcing tournaments. Now, at this point, I've told you that if you are locally forcing, how you need to look like. On the other hand, I've told you locally forcing tournaments exist, but our main result is actually much stronger than both of these things. It also lies behind the proof of both theorems that I told you so far. So it's a general characterization of whether a fixed tournament H is locally forcing or not, depending on certain algebraic conditions. So now I want to introduce these algebraic conditions, and then I'll tell you our main result. So both algebraic conditions arise quite naturally from some examples which are natural candidates for counterexamples to local forcing. So the first one we call Tn alpha. So this is a random tournament where on n vertices, where we fixed an ordering of the vertices and then oriented every edge to respect the ordering with probability alpha and to not respect it with probability 1 minus alpha. Okay? So now, since we want to look at this for sources of counterexamples, what we actually care about is how many copies of some fixed tournament H do we see in this kind of example. And also, I should point out that if, for example, if you plug in alpha equal to 1/2, you just recover the usual random tournament. Very good. So now this expectation definition depends on n. And I did not put an n here. And the reason is, if you actually compute this expectation, which is just an elementary calculation which I'm going to skip, you get this expression on the right here. And really, in this talk, I'm not going to care what the expression on the right is. Really, the only thing I care about it is that it only depends on the tournament H. It does not care what n was. Okay? So now I'm ready to give you the first of our algebraic condition. We call it T-clique forcing, and we say that a tournament H is T-clique forcing if its polynomial pH is never equal to its value at 1/2 except at the 1/2 itself. So don't worry too much about what this is actually saying. So this is an algebraic statement which is convenient to work with. But if you think a little bit and translate this part of the definition back to what it actually means in this statement, what T-clique forcing means is that H is T-clique forcing if, when you know that Tn alpha has correct counts of H, then this implies that Tn alpha needs to be quasi-random. Or in other words, it implies that alpha should be equal to 1/2. This is why 1/2 appears in this statement here. Or in other words, if this is a little bit informal but you can make it precise, what T-clique forcing is actually saying is that it is a special case of local forcing in which you restrict attention only to this special tournament's Tn alpha. Okay? Very good. So this is the first algebraic condition that I have, and the important bit is this morally correct definition of T-clique force. Now the second algebraic condition arises in a very similar way. So we say that a tournament is T-beep forcing so I need to first define the random object from which it arises. So for me, this is going to be TNN alpha, which we define to be the random tournament to consist of two copies of the random tournament TN1 half, which we orient independently. And then we orient each edge to go from left to right with probability alpha, and to go from right to left with probability 1 minus alpha. So this just gives us another random tournament, which is a potential source of counterexamples. So now in this setting, the story is a little bit more complicated. There is more than one of these polynomials which control how many copies you actually see in this picture. So PHA is defined as the expected number of copies of H you see in this picture, which have A vertices in the left part and H minus A vertices on the right. And once again, an elementary calculation, expectation calculation, tells you that these PHAs don't depend on N, so on the size of this model at all. Okay, so now once again, we can define a similar algebraic statement, which says that a tournament is said to be T-beep forcing if there is no alpha different than a half, for which all of these polynomials, they simultaneously evaluate to their value at a half, at alpha. Okay, so once again, this is a bit messy and hard to grasp in a talk, but really you can translate this into saying that T-beep forcing is a special case of local forcing in which you restrict attention only to the tournaments which look like this. So which arise from TNN alpha for different values of alpha. Very good. So now I'm finally ready to tell you our main result, and it's about time. So let me remind you here again what it means to be locally forcing. So it means that if you have correct local counts of H, then you are quasi-random. Okay? So now T-clique forcing is just a special case of this when you restrict attention to this model Tn alpha. T-beep forcing is once again a special case of local forcing when you restrict attention to these tournaments Tn alpha. And now what is remarkable is that the implication goes the other way around. So you are locally forcing if and only if you are both T-clique forcing and T-beep forcing. Now, what is remarkable about this is that in order to check whether you are locally forcing, the only thing you need to do is look at these very special cases, Tn alpha and TNN alpha, and check whether they give you counterexamples. And the algebraic statements from the previous two slides that I gave you are precisely quantifying whether you can find a counterexample or not. Very good. So this is our main result. And actually, it allows you for a fixed tournament H to figure out whether it's locally forcing in a very simple way. So let me describe how you do this as a concluding remark, and then give you some open problems. So an algorithm for testing whether H is locally forcing based on this equivalence result that I've just told you goes as follows. So there is an algorithm called Sturm's algorithm, which allows you to tell how many distinct roots a polynomial has in a closed interval. Okay? So if we apply it to this polynomial pH, if we have only one root, so 1/2, which we know is a root, then you are T-clique forcing. If you have more than one root, you are not. So this algorithm immediately tells you, lets you check whether you are T-clique forcing or not. And the same game you can play with this T-bip forcing polynomials. But now you have more polynomials, so there is an extra step. So you are wondering whether a certain number of polynomials have a simultaneous root. And here you use Euclid's algorithm to find the GCD, and then you use Sturm's algorithm on this GCD, and this tells you whether you can find a simultaneous root of these polynomials in our interval 0, 1 or not. And in particular, how many distinct ones you get. We know that 1/2 is going to be a common root, but we're wondering whether there is another one. So this lets you check T-bip forcing. So just by doing this, you check T-clique forcing, you check T-bip forcing, you immediately can tell whether you are locally forcing or not. Okay, and now my first question is whether you can find a polynomial time algorithm for testing whether you are locally forcing. And so actually Sturm's algorithm and Euclid's algorithm, both of them are polynomial time. You can do this quickly. So the problem here is actually computing our polynomials efficiently. So they're defined through all possible orderings of the vertices of H, of which there are H factorial. So doing it naively, you cannot do it in polynomial time. But for example, for these guys, I think we can compute them in polynomial time by being a little bit more clever and using some kind of dynamic programming. So this is so really what this question is asking is whether you can compute these two polynomials in polynomial time. Very good. A second question that I want to ask is whether a uniformly sampled random regular tournament is locally forcing or not. So here, why is this model a natural candidate? If you remember our restrictions, we wanted a nearly regular tournament, which is strongly quasi-random, which a uniformly sampled random regular tournament should satisfy. However, since you don't have independence between edges, it's much harder to work with this model and our polynomials. So we actually don't know how to do this, but we strongly believe that it should be true. That with high probability, uniformly sampled random regular tournament is locally forced. And the final question is, T-bip forcing is, I claim, a very, very weak condition. Why? Because it requires some H relatively arbitrary polynomials to have a simultaneous root, which if it ever happens, sounds to me at least like quite an algebraic coincidence. So, and we actually don't know of a single example of a tournament which is not T-bip forcing. So the nice part of this question is that if you can show that there are no not T-bip forcing tournaments, then from our equivalence, you can just remove the T-bip part. And you can only check this one special case, T-clique forcing. And actually, if you think a little bit, this question is the correct analog in the tournaments of the conjecture of Simonovits and Sós from the induced setting. So it would take me a bit of time to explain why this is the case. So I'm not going to do it here, but I just want to mention that I really think this question is interesting. That's all that I had to say. Thank you very much for your attention. That's it.
Thank you, Matija. I will unmute everyone. Let's try to give a round of applause to Matija for a great talk. And for the question period, Let me mute everyone again. Okay, so for the question period, now if you have any questions, please write in the chat box and then I will unmute you and you can ask your question. So, any questions? Alexei has a question, so 1 second. For some reason, I cannot unmute Alexei.
Hey, can you?
Oh, okay, great.
Hi, Matija. Could you draw us the 5-vertex exception tournament? Thanks.
So actually, I think don't hold me too much.
Is it the one you had done before?
If I
It's the same one. Okay.
Here.
Yeah, I was wondering. Okay, thanks.
No. Thank you for the question.
Any other questions?
Okay.
Honza has a question. So Honza, do you want to ask?
Yes, so my question is whether you can, I think at least in graphs, there are some results, but that you know, sometimes it's enough to test over sets of a given size, right? So you don't have to test over all linear sized sets, but say over sets of size 0.1. And so if you can say anything in that direction.
So thank you for the question. It's a good question. I've actually not thought about it, but I think it should pretty much everything that I'm saying should stay correct. So of course, this is a weaker restriction than local forcing. So I'm thinking whether at any point we actually need that. So I think for the direction, so the proof of our main result goes through regularity lemma and some acrobatics that is happening there. And I think that should still work even if you just allow me to use sets of prescribed size. But since it's regularity lemma, I'm not going to claim this without actually checking. So I think it does work, that it's enough to just have a fixed size and that this equivalence theorem is still going to hold. But I would need to run the computations to actually see if somewhere we are actually using the power that we can take any linear size subset. Thank you for the question. It's a great question.
Dan had a note. Let me unmute him.
Sure.
Dan, you can speak now.
No, I think it's just a remark, but I think the tournament is almost what Matija was showing, but I think the blue edges are slightly oriented differently. But I'm not 100% sure.
I was doing it by memory, I must admit, so it's possible when doing
I also rely now on my memory, so.
Sure. So it doesn't really have any specific reason why it should be globally forcing. At least I don't see.
Yeah, I also don't see any.
Nice. Any other questions? If not, I'm going to again unmute everyone, and please let's give another round of applause to Matija for the talk and answering all our questions.